Welcome to this coding walkthrough. In this session, we will explore LeetCode problem number 1528, shuffle string. The goal is to rearrange the characters of a string based on the given indices array. We'll discuss the problem requirements, work through an efficient solution, and analyze its complexity. Let's dive in. In this problem, we are tasked with shuffling a string based on a given array of indices. Specifically, we are given a string s and an integer array indices, both of the same length. The goal is to rearrange the characters in the string such that the character at position I in the original string is moved to the position specified by indices I. Once all the characters are rearranged, we return the resulting shuffled string. For the input format, s is a string consisting of lowercase English letters and has a length n, where n can range from 1 to 100,000. The array indices is also of length n, and contains unique integers between 0 and n1, ensuring that every position in the string is accounted for. The output is simply the shuffled version of the string, created according to these rules. Let's look at the first example to understand how this works. Here, the string s is code, and the indices array is 3, 1, 2, 0. The output is eddoc. To see why, consider that the character c at index 0 in the original string is moved to position 3 in the shuffled string. Similarly, o at index 1 moves to position 1, d at index 2 moves to position 2, and e at index 3 moves to position 0. Rearranging the characters in this way gives us the final shuffled string eddoc. In another example, if the input string is ABC and the indices array is 0, 1, 2, the result is simply ABC, because each character is already in its correct position based on the indices. To further clarify, in the second example, the indices array directly maps each character to its original position, so no rearrangement is needed. Now, consider a third example where the string s is ion and the indices array is 3, 1, 4, 2, 0. The output in this case is nihao. Here's how it works: the character at index 0 moves to position 3, I at index 1 moves to position 1, O at index 2 moves to position 4, H at index 3 moves to position 2, and N at index 4 moves to position 0. After rearranging the characters based on these indices, the resulting string is nihao. The shuffled string in the third example is therefore nihao. To summarize, the problem includes several constraints to ensure correctness and efficiency. The string s and the indices array are always of the same length, and the length n can range from 1 to 100,000. All characters in s are lowercase English letters, and all values and indices are unique, ensuring no duplicate mappings. Potential edge cases to consider include when the input string has only one character, where the output would simply be the same single character, or when the indices array already represents the correct order, meaning no shuffling is needed. Additionally, the function must handle large inputs of up to 100,000 characters efficiently, and scenarios like reversed order in the indices array, where the string must be completely reversed, should also be handled correctly. These constraints and edge cases are key to implementing a robust solution for the problem. To solve the problem of shuffling a string based on the given indices array, we can start by considering a brute force approach. The intuition here is straightforward: for each character in the string s, we use the indices array to determine its target position, and then place it into a new array. By the end of this process, the new array will represent the shuffled string. Here's how it works step by step. First, we initialize an empty array called result with the same length as the string s. Then, we iterate through each index in the indices array, and for every index I, we place the character s, I, into the position indices, I, in the result array. Finally, we join the elements of the result array into a single string and return it. This approach is efficient with a time complexity of O, n, as we only loop through the indices once, and a space complexity of O, n, since we need the extra array to store the intermediate results. While the brute force approach is simple and effective, it does have some downsides. Most notably, it requires an additional array to store the intermediate results, which increases memory usage. To address this, we could explore an in-place shuffling method. The idea here is to rearrange the characters of s directly in place without using an auxiliary array. However, this approach introduces several challenges. For example, we need to carefully track which indices have already been visited to avoid overwriting characters prematurely. Additionally, handling cyclic dependencies in the permutation can be tricky and error-prone. From a performance standpoint, the in-place approach can also be less efficient. In the worst case, repeated swaps may result in a time complexity of O(n) squared, although it does save space with a space complexity of O(1). Overall, while this method is intriguing, it is harder to implement, more prone to bugs, and less practical for larger inputs. Instead of the complexities of an in-place approach, we can focus on an optimized solution that builds on the brute force method while emphasizing simplicity and clarity. The key observation here is that the indices array provides a direct mapping from the original positions of the characters to their target positions. By leveraging this mapping and using an auxiliary array, we can ensure the shuffling process remains straightforward. The steps are as follows. First, we initialize an empty array result with the same length as the string s. Then, we iterate through the indices array, placing each character s, I, at its corresponding position indices, I, in the result array. Once all characters are placed, we join the elements of the result array into a string and return it. This approach maintains an efficient time complexity of O(n), as we only iterate through the indices once, and a space complexity of O(n), due to the auxiliary array. By keeping the implementation simple and avoiding unnecessary complications, this solution strikes a balance between clarity and performance. When comparing the different strategies, the brute force and optimized approaches stand out as the simplest and clearest options. The optimized approach, in particular, avoids the pitfalls of the in-place method, which, while saving space, is challenging to implement and inefficient for larger inputs due to its quadratic time complexity. Ultimately, the optimized approach was chosen as our solution because it balances simplicity, efficiency, and clarity. While it does use additional memory for the auxiliary array, this trade-off is reasonable given the linear time complexity and straightforward implementation. The in-place approach, though conceptually interesting, is simply not worth the added complexity and performance drawbacks for this problem. By focusing on readability and efficiency, the optimized approach ensures a reliable and robust solution to the shuffle string problem. In this problem, we are given a string s and an array called indices. Our goal is to rearrange the characters in the string so that each character in S is moved to the position specified by the corresponding value in the indices array. For example, if S's code in indices is 3, 1, 2, 0, the output should be the rearranged string eddoc. To solve this efficiently, the first step is to initialize an empty array called result with the same length as S. This array will temporarily store the rearranged characters at their correct positions, which allows us to directly place characters without unnecessary shifting or extra computation. This step helps simplify the process and prepares us for the next part of the algorithm. The next step is to loop through the indices array using a simple for loop. For each character in the string S, we determine its target position using the indices array. Specifically, for each index I, the character at S, I, is placed in the position indices, I, of the result array. This operation ensures that each character is directly placed in its correct location without any extra computation. Once all the characters are placed, we can combine the elements in the result array into a single string using Python's join method. This method is not only straightforward but also efficient for merging characters into a contiguous string. After joining the result array, the algorithm simply returns the final string. This approach ensures we handle the shuffling process in an optimal manner, both in terms of time and space complexity. The space efficiency of this approach is noteworthy because the only additional data structure we use is the result array, which has the same length as the input string, making the space complexity O(n). The algorithm relies on three key data structures: the input string S, the indices array that defines the target positions, and the temporary result array that holds the characters during the rearrangement process. To better understand how this works, let's break down the example where S's code in indices is 3, 1, 2, 0. We start by initializing the result array as, Then, as we iterate, we place each character into its corresponding position. For instance, the character C from S0 is placed at result 3, and so on, until all characters are correctly assigned. At the end, the result array looks like E, O, D, C, which can then be joined into the string eddoc. The process of joining the result array into a final string is efficient and straightforward, resulting in the output string eddoc. This is the string that gets returned as the solution to the problem. Now, analyzing the complexity, the algorithm iterates through the string S exactly once, which takes O(n) time, and each character placement into the result array is an O(1) operation. The final step of joining the result array into a string also takes O(n) time. Therefore, the total time complexity of the solution is O(n). For space complexity, the primary additional storage we use is the result array, which has the same length as the input string, making the space complexity O(n) as well. This ensures that the algorithm is efficient and scales well even for larger inputs. When considering edge cases, the algorithm handles them gracefully. For example, if the input string S is empty and the indices array is also empty, the algorithm simply returns an empty string since there are no characters to rearrange. Similarly, for a single character input like S equals and indices equals 0, the output will be a, as there's no change required. The problem guarantees valid input, meaning we don't need to handle scenarios with duplicate values in the indices array. The Python implementation of this algorithm is both clean and concise. We initialize the result array, iterate through the string to place characters in their correct positions, and then join the array to produce the final output. This implementation adheres to the outlined steps and ensures optimal time and space complexity, making it a robust and efficient solution to the problem. The goal of this solution is to rearrange the characters of the string S according to the indices array provided. Here's a step-by-step explanation of the code. 1. Initialization of the shuffled list. We start by creating an empty list called shuffled with the same length as the input string S. Each element is initialized to an empty string. This list will eventually hold the characters of S in their correct positions. 2. Main loop to assign characters. We iterate through the string S using a for loop. For each character in S, we determine its target position by looking up the corresponding value in the indices array. We then place the character from S at the correct position in the shuffled list. For example, if indices I is 3, the character S, I, will be placed in shuffled 3. 3. Joining the list into a string. After populating the shuffled list, we use the join method to concatenate all its elements into a single string. This gives us the rearranged version of S, which is returned as the final result. Example walkthrough. Let's take an example. Input S equals code, indices equals 3, 1, 2, 0. Step-by-step execution asterisk. Initialize shuffled equals, Loop through each character of S. I equals 0, place S, 0, equals C at shuffled, 3, so shuffled equals, C. I equals 1, place S, 1, equals O at shuffled, 1, so shuffled equals, O, C. I equals 2, place S, 2, equals D at shuffled, 2, so shuffled equals, O, D, C. I equals 3, place S, 3, equals E at shuffled, 0, so shuffled equals, E, O, D, C. Join shuffled into a string, edoc. Output, edoc. Complexity analysis. Time complexity. The algorithm processes each character of S exactly once, so it runs in O(n) time, where n is the length of S. Space complexity. The solution uses an additional list shuffled of size n, resulting in O(n) space usage. This is optimal for the problem. This implementation is efficient, straightforward, and handles all edge cases, such as an empty string or duplicate indices, effectively, although the latter is guaranteed not to occur as per the problem constraints. This is the Java implementation of LeetCode problem number 1528, shuffle string. The solution mirrors the Python logic by using a char array to place characters at their specified indices. Key differences include explicit type declarations, the use of char instead of a list, and the string class for manipulation. The method iterates through the input string and assigns each character to its correct position in the result array, which is then converted back to a string. To solve the problem, we need to recreate the string based on the provided indices. For the input string code and indices 3, 1, 2, 0, we first initialize an empty list called shuffled with the same length as the string, which is 4. So, we start with shuffled equals, In the first iteration, we take the character C from S, 0, and place it at position 3 in the shuffled list, as indicated by indices, 0. This updates shuffled to, C. In the second iteration, we take the character O from S1 and place it at index 1, as specified by indices 1, resulting in shuffled equals OC. Next, during the third iteration, we take the character D from S2 and place it at index 2, as specified by indices 2. This updates the shuffled list to O, D, C. Then, in the fourth iteration, we take the character E from S3 and place it at index 0, as specified by indices 3, updating shuffle to E, O, D, C. Finally, we join all the elements in the shuffled list to form the output string, which is EOC. This completes the process for the first example, and the result matches the expected output. Now, let's consider a second example where the indices are reversed. For the input string ABC in indices 2, 1, 0, we start by initializing shuffled as, comma, comma. In the first iteration, we take the character A from S0 and place it at index 2, as indicated by indices 0. This updates the shuffled list to, comma, A. Then, in the second iteration, we take the character B from S1 and place it at index 1, as specified by indices 1. This updates shuffled to B, A. During the third iteration, we take the character C from S2 and place it at index 0, as specified by indices 2. This updates the shuffled list to C, B, A. At this point, we have placed all the characters in their correct positions based on the indices. The last step is to join the elements of the shuffled list, resulting in the string CBA. This is the final output for the second example, and it demonstrates how the algorithm works with reversed indices. In this third example, the indices are already in the correct order. Given the input string Leet in indices 0, 1, 2, 3, we initialize the shuffled list as, comma, comma, comma. In the first iteration, we take the character L from S0 and place it at index 0, as indicated by indices 0. This updates shuffle to L, comma, comma. In the second iteration, we take the character E from S1 and place it at index 1, as specified by indices 1, resulting in shuffled equals L, E, comma. Next, in the third iteration, we take the character E from S2 and place it at index 2, as indicated by indices 2. This updates shuffle to L, E, E. Finally, in the fourth iteration, we take the character T from S3 and place it at index 3, as specified by indices 3. This updates shuffle to L, E, E, T. Since the indices were already in the correct order, the shuffled list now matches the input string. Joining the elements gives the output string Leet, which confirms that the algorithm works even when no reordering is needed. To analyze the time complexity of our solution for the shuffle string problem, we can break it down into three main components. First, we initialize a list called shuffled with the same length as the input string S. This operation involves allocating memory for the list, which takes n time, where n is the length of the string. Next, we process the string S using a for loop. This loop iterates over each character in S exactly once, and for each iteration, the statement shuffled indices I equals S, I is executed. Since both accessing and assigning to a specific list index are O1 operations, the total time for this loop becomes O(n), as it runs n times. Finally, we join the shuffled list into a single string using Python's join method. This operation also processes each character in the list once, giving it a time complexity of O(n). Adding up these contributions, the overall time complexity of the solution is O(n) plus O(n) plus O(n), which simplifies to O(n). Thus, the total time complexity of the solution is O(n). Now, let's consider the space complexity. The inputs S and indices are provided as part of the problem, so they don't count toward the algorithm's additional space usage. However, the algorithm does allocate some additional memory. First, the shuffled list is created, which has the same length as the input string S, requiring O(n) space. Next, when we join the shuffled list into a single string, the join operation generates a new string in memory to store the result. This also requires O(n) space. Combining these contributions, the total additional space usage is O(n) for the shuffled list and O(n) for the final output string, resulting in an overall space complexity of O(n). Let's compare this optimized solution to a naive approach. In a brute force method, one might repeatedly search for the index of each character in the indices list and build the string incrementally. This would require O(n) time for each search, performed n times, leading to a time complexity of O(n) squared. However, even in this approach, the space complexity remains O(n), because the final string and any intermediate storage still depend linearly on the input size. By contrast, the optimized solution avoids repeated searches by directly indexing into the shuffled list, completing the task in a single pass. This reduces the time complexity to O(n), while maintaining the O(n) space complexity. When analyzing best, average, and worst cases, all scenarios yield O(n) time complexity because the algorithm processes each element of Sn indices exactly once, regardless of the input values or their arrangement. To solidify this analysis, we can look at the mathematical reasoning behind the big O notation for our solution. Each character in the string S and each index in the indices list is processed exactly one time. This means the number of operations scales directly with the size of the input, making it proportional to n. Furthermore, operations like list indexing and string joining do not introduce any higher order terms, they are bounded by O(1) and O(n), respectively. When we sum up the contributions of all steps initializing the shuffled list, iterating through the input, and joining the list into a string, the overall complexity remains O(n). The same reasoning applies to space complexity, as the algorithm allocates memory linearly with the input size. This mathematical proof confirms that both the time and space complexity of the solution are optimal at O(n). When working on the shuffle string problem, there are a few common mistakes to be mindful of. First, attempting to modify the input string S directly can lead to issues, especially in languages like Python or Java where strings are immutable. Instead, you should create a separate array or list to construct the shuffled result. Another frequent source of errors is misunderstanding the indices array. Remember, indices I indicates the target position for the character at S, I, not its current position. Additionally, it's important not to overlook edge cases. Examples include an empty string, a string with only one character, or scenarios where the lengths of Sn indices don't match. Although the problem usually guarantees valid inputs, thorough testing is critical. Lastly, avoid inefficient solutions like nested loops or repeatedly searching for indices, as these result in unnecessary O(n) squared complexity. Instead, aim for a direct assignment approach that achieves O(n) efficiency. Another potential pitfall is index out-of-bounds errors. While competitive programming problems often guarantee valid constraints, real-world applications might not. Ensuring that all indices values are within the valid range of 0, len, s-1 is a good habit to develop. From an interview perspective, this problem is a great opportunity to demonstrate pattern recognition. It highlights the importance of mapping relationships between two arrays, a concept that frequently appears in string and array manipulation challenges. Additionally, interviewers often emphasize the efficiency of your solution. Make sure you can explain how your approach achieves O(n) time complexity by directly assigning characters to their target positions. Lastly, showing awareness of edge cases, like handling empty or minimal input, reflects a thorough and detail-oriented mindset, which is something interviewers value. This problem shares similarities with a number of related challenges, which can help you build a broader understanding of key concepts. For instance, LeetCode number 1, toSum, also involves mapping relationships, in this case between indices and values. LeetCode number 152, maximum product subarray, focuses on the efficient traversal of arrays, which is another essential skill. LeetCode number 283, move zeros, is an excellent example of rearranging elements within an array while maintaining efficiency. Finally, LeetCode number 1347, minimum number of steps to make two strings anagram, involves character mappings in the context of string manipulations. Exploring these problems can help reinforce the patterns and strategies applicable to the shuffle string problem. There are also alternative approaches to solving the shuffle string problem, each with its own trade-offs. The most common method involves using additional space by creating a result array of the same size as S. For each character S, I, you place it at result, indices, I. This straightforward approach ensures O(n) time complexity but requires O(n) space. A more advanced technique involves in-place shuffling, where you modify the string directly by swapping elements to their correct positions. While this saves space, it increases code complexity and can be harder to debug. Another option is a sorting-based approach, where you pair each character with its target index, sort the pairs by index, and then reconstruct the string. This method is conceptually simple but comes with an O, n log n, time complexity, making it less efficient compared to other solutions. Finally, it's important to consider the trade-offs between different solutions. The optimal approach, which uses a result array, balances efficiency and simplicity with O, n, time and space complexity. In contrast, in-place shuffling saves space but complicates the implementation, making it more prone to errors. Sorting-based solutions, while easier to explain and understand, are less efficient due to their O, n log n, complexity. When deciding on an approach, consider the specific requirements of the problem, such as whether space optimization is critical or if readability and maintainability are more important. Making these trade-offs thoughtfully demonstrates a deep understanding of algorithm design and problem-solving strategies. Great job! We've covered the solution to shuffle string, discussing the algorithm, time complexity, and key insights. Remember, index mapping is a crucial concept that can be applied to many similar problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!